want to go through everything I read.
I already went through everything. Great. I'll leave it.
All right, I'm going to start recording. I am going to call someone, and then we'll go over the bell work and do today's lesson. All right. So,
I have to go back and do things and it was not great. But I will see when I start on
the board decided. All right, headphones off at this time, please. We are getting started with the lesson. Today's lesson, actually, it should not be super long, just like last class's lesson. And I have a game review of functional groups I want to do afterwards. So we'll be.
Is it great? My question is what's.
Oh, thank God.
You'll find out.
As long as it's not graded, I'm okay.
I just want.
I don't
You
know.
need to practice them.
I just want one.
You need to practice them. I know you want one game. I know what game that is. I do have it on there. So one of the days we can do a gym kit. But I wanted to try something else, so we'll see what we have time for. All right, so let's get started with calling for the bell work. I did say you need 5 out of 6 here. I did check a bunch of you that had it upon request. Alex does not get called today because he got called last time. Try to keep it one person, one per week. Rosalind does not get called to the 2 people. All right. Go. You said okay. So 1. Oh, 3. 3. Yeah. Sorry. It's okay.
It's organic.
Okay. So it's okay. Next time. Good next time. All right. So let's go over the answers and see what happened. First thing to note is to do a quick little reteach of condensation, polymerization. That was the only new type of polymerization we learned last class. And basically it's removing water or HCl from individual molecules and then bringing them together. So it's removing HOH, water, or HCl from monomers, which are the individual units, to create polymers. That's the idea of what a condensation polymer is. And then there were specific groups we would look for to know what to remove. And I gave like a specific slide on that because I think it's really important that you're able to identify the different groups. And so you would remove OH from a carboxylic acid, COOH. You would remove hydrogen from either an alcohol or an amine. So either an alcohol or an amine. And then you may, and I believe we'll see it today, have to remove Cl, chlorine. And you would only remove chlorine if you have something called an acyl chloride, which is COCl. So these are the specific things that you're looking for to remove the small molecule. So if you have a carboxylic group, you're going to remove OH. If you have an alcohol or an amine, you're going to remove H. Together, if I remove an OH and an H, that makes water. So looking at this question, they give you something that becomes a polyamide. Amide is always CON. So you may want to write that down. I believe I brought it up last lesson. But whenever you have an amide, that's actually a new functional group for A level, it's going to have this. The CO and the N, con. That's an amide. And then you have whatever other R group. So looking at this molecule, F, what type of functional group is that? The carboxylic acid. which means we would have to remove an OH from it. So when you're trying to put together what happens, it may help to first write everything displayed. It makes it easier to see what you have to do. And so I'm going to rewrite this displayed. So I've got this, and I've got this. And what am I supposed to be trying to merge this with? This one, right? Here, I'm going to display the N, H, H, and then this is another, it's called benzene. It's cyclohexane with 3 double bonds. And then I've got the N, H, H, and the OH down here. So then what do we have to do in this process? So the first thing I would do is I would fully display my groups so I know what I need to remove. I'm going to change colors. From the inside first, what am I removing from the carboxylic acid? It says remove the OH. So I'm going to put a little box around that so I know what I'm doing. On the amine, I'm going to remove a single hydrogen because together that forms water. So I know these two things are going to leave, and instead this carbon's going to connect with this nitrogen. On the outside, I also need to remove water. I double checked the textbook while you all were working on home, like the classwork last class, and they do allow you to basically just erase that, erase this, and then do the dingling bonds with the N. So that's what you're going to see me do. Take the OH away from here, take the H away from there, and then write the dangling bonds afterwards. So now this is my creation of what I need to put together. Now I'm going to rewrite everything. So I write myself a little arrow so I know what I'm doing, like that I'm putting this together to form. And now I'm going to write same thing. CO, but that OH I took away. So what am I going to put on the outside? A dangly little line saying that this continues over and over again. And then I'm going to write my benzene. So what you're going to notice is this process is tedious. There's a lot of atoms to keep track of. And just like everything in A-level chemistry, if you miss one atom or write one too many hydrogens and break the octet rule at any one spot, guess what? The whole thing is wrong. So you've got to be kind of meticulous here as you're going through. And so this is CO. This water gets removed. So the next thing I'm supposed to write is the nitrogen. And then I write that little hyphen because the one at the top I've removed. And then I write the rest, which is this. The OH here, and then I know that this was connecting at the nitrogen because it's an amide that I'm making, and so I do that. Remove one of the hydrogens and instead take the line out right and left. Where are the 2 marks? One of them was for the outside with a little N. The other one is the fully displayed amide bond, which means the C double bond O and N. You have to show that exactly. If you just write that structural or skeletal, they will not give you the mark. And they said it here, should be shown displayed. Displayed means show all the covalent bonds. The same thing as almost the Lewis structure, pretty much. The only thing is you don't have to write all the valence electrons. If you want to, you could. This would be the rest if you wanted the valence electrons there. And then, but they don't require that you include the valence electrons. At this point, they expect you to know that oxygen will always only make 2 bonds and nitrogen will make 3 bonds. Does that make sense? Because oxygen's in group 16, so it can only connect twice, whereas nitrogen's in group 15, it can connect 3 times. So they expect you to know that. They don't need you to write the electrons, but you can if you want. Just don't write them wrong if you do include them. All right, are we good with this? Take a picture if you didn't get it down, because this is actually hyper specific in how they want it to be done. And this part up here is super important because if you understand this, remember how there were like 6 objectives? Those 6 objectives are like right here. Literally, it covers every single type of polymerization you can have. It just really depends on what functional group you have. And that's one of the things you're going to notice is a running theme, especially in the organic portion of this class. It looks like it's more than it is. Like the standards suggest that it's more, than what you're actually looking for. If you just know a few key things, you can solve a lot of questions here. Ready to continue? All right, this one. Addition polymerization is something that we looked at back in AS. So let's just review it real quick. Ethene, which is this one, going to polyethene. What did we do for addition polymerization? We would break the bond in the middle and extend it out. That bond is called a, what type of bond? The bond that we would be breaking? Called a pi bond. So the bond broken is called a pi bond. And then when we form these two new lines to form our little polymer, here it is. Not too much that we have to write. What are these new bonds? They're the first bond that connects two atoms together, so they are called sigma bonds. So it's sigma bonds only. So remember that single bonds are sigma bonds, and double and triple bonds are pi bonds. That is actually something that predates organic. We learned that back more in the beginning of AS chemistry when we were learning about compounds and intermolecular forces. We also learned about this topic of sigma pi bonding. Hybridization, remember that thing, sp2, sp3, was actually heavily featured on last year's paper 4. The students were surprised. So all these old topics, they are going to come back. We are going to review them in practice questions as we go along, because some AS topics can show up on the A-level exam, and that could be welcome for you, or that could be scary. But we need to review AS topics as we go along. All right, continue. Last 2. Another AS topic, intermolecular forces. I did put a couple questions in the homework, or at least one on the homework of intermolecular forces that I found. Here they're asking you for 2 intermolecular forces and what groups would have those intermolecular forces. I had picked, and many of you did as well, hydrogen bonding, and what would have been doing the hydrogen bonding? NH, because it has to be hydrogen connected to F, O, or N. It has to be with bond. So we would say NH is the group involved with the hydrogen bonding. And then I picked this the second permanent dipole. And the group involved with that would be the C double bond O. Could you have also said dispersion? And if you had, the group interacting with that would have actually been the benzene ring itself. So, because that's just C and H. So you could have said dispersion forces or instantaneous dipole-induced dipole, or IDID, if you had picked the benzene ring. So they're just asking for 2 of the intermolecular forces that are present there and what groups were responsible for the creation of that intermolecular force. If you got both of those, you got 2 marks. But you did have to get both the hydrogen bonding and the correct group identified with it in order to get the mark. All right, so today, what are we covering? We are covering hydrolysis, which is the opposite of condensation. I don't know if you remember back in AS chemistry, with almost all the organic reactions, most of the reactions were inverses of each other. Addition and elimination were inverses of each other. Oxidation and reduction are inverses of each other. Hydrolysis and condensation are inverses of each other. And so today we're going to be looking over hydrolysis, and we're also going to be looking over biochemistry a little bit. A lot of the biochemistry segments of this class have been taken out and can mostly be found in AS biology. But a couple of topics remain, and those topics are actually mainly in today's lesson and in this unit of study. And so the first thing we're going to look at is hydrolysis. Just to recall, hydrolysis, what does that mean again? What does lysis mean? It actually means to break apart or tear apart. So you should underline that word. Lysis, whenever you see it in biology, you see it in chemistry. Lysis means to break apart. And then the hydro part means with water. So in the process of hydrolysis, you're actually going to be putting water into a large molecule to break it apart. So you would either be starting with an amide or an ester or an acyl chloride. So something here, and you'll break it apart with water. So you start with these and then you tear them apart all at these specific spots. And I'll bring up where the specific spots are. Here, here, and here. And so again, if you recognize the key component, what's breaking off, you'll be able to identify what to do. And so this is just to begin. We'll go over the objectives and then we'll get to business. I believe this lesson is an hour or less, like the last one. We'll start with hydrolysis and then get to the biochemistry. Let's take a look at the objectives. If you need more time, I can let me know when you're ready. You'll see some writing. You're going to recognize the reactions once you see them from last year. You may remember when we said ONA a lot. We'll be revisiting ONA today. A little bit more easily every day. Rosalind, while I'm waiting, there is a field trip opportunity on February 14th. It's an A day for 11th and 12th graders to go to Miami-Dade College. They're doing a STEM presentation, some undergraduate research they're talking about, and they're going over AI, and they're going to have a virtual reality exercise that you guys could do. Would you like to go? I'm offering to this class first. I offered to this class first last class because I'm gone for that day. Like I'm chaperoning the field trip. So it would be it's from 9 a.m. to 1 p.m. and it's at Homestead campus. It's free. Would you like to go? Okay, I'll put your name down. That's the reason. No. So we'll have a short class that day. We will have like a partial class, but we'll have a short class that day because we're leaving out of this class. Oh. And then we're coming back at 1 p.m. This is an ester, yes. Notice that all of these groups have the same feature. They all have a carbonyl group next to an electronegative atom. This is a carbonyl group. Nitrogen is electronegative. This is a carbonyl group. Oxygen is electronegative. This is a carbonyl group. Chlorine is electronegative. So every single one of these groups that you would hydrolyze have the same technical key feature, atomically speaking. So that's why I said, instead of memorizing so many different things, if you can group ideas together, it's going to make these topics so much easier to get through. And so let's go ahead now and go through these standards. It's not a ton today. Like I said, I was reviewing the lesson last night and I was like, oh, this one isn't that long. But there are still some really important things we need to go over. I know that a couple students will be out on Monday. We will be covering a lesson that day, but you'll have to catch up. Next Friday, I will not do a new lesson because of the field trip. But next Monday, there will be a new lesson. And it will be the final part of polymerization and starting analytical techniques. All right, so let's take a look at the objectives. First one, describe the acid base. Oh, are we going back to acids and bases? Yes. I actually had to leave some questions out of the quarterly because it actually covered this. It was acid basis, but it was with this topic. So I haven't taught that yet, so I'm not gonna include those questions yet. But describe the acid-base properties of amino acids and the formation of something called as somebody in the class was a German last year, but they would get mad at me if I said it wrong. But it's called a Zwitter-ion. It has a German background, but it's a Zwitter-ion, and that's the. But it's called a Zwitter-ion. You can look online to see how it's said correctly. But it is a ZW, Zwitter-ion, to include the isoelectric point. And so we'll go over what all of that is today. It says describe the formation of amide bonds, which are also called peptide bonds, which if you studied biology, you have already seen how to describe peptide bonds between amino acids to give something called a dipeptide and a tripeptide. So we'll be doing that today. Interpret and predict the results of electrophoresis. This will actually be on Monday's lesson because that's where we're going to start the analytical techniques. So these first two we're doing today. The third one we'll do. And then the degradable polymers we actually did last class. So we don't have a ton of objectives to cover today because we did cover some of this already. But we do also have, I didn't include the objectives for hydrolysis. We do also have to cover hydrolysis today, which we're about to get to now. So there are two functional groups that are technically new that you need to memorize. One of them is called an acyl chloride. It looks like a carboxylic acid, but instead of the OH, it has a Cl. We call this an acyl chloride, and you do need to memorize it. And the second one is called an amide. And so you not only need to memorize them, you also need to know how to name them. And so to name an acyl chloride, you would end it with oil chloride. So this one right here is ethanoyl chloride. And then here for amide, you would actually end with amide in its name. So if we said that this was just one CH3, like if this was CH3O NH plus NH2, this is 2 carbons long. So this would be ethanamide is the way you would say it. So just so you have the endings for these two functional groups. So I always think that these chlorides are fun because they end with oil chloride. They'll sound funny when you say them. And then the amides just end with amide. So why do chemists use acyl chlorides? They're more reactive than carboxylic acids. So they are a great starting point for all kinds of chemical reactions. And so these are often used in chemical reactions. And then amides formulate the basis of many of your biochemical groups, like groups that are in the body. So that's why both of these will be studied. So what do you have to do with these? Memorize. You did not need to know these functional groups last year. They were left out of the AS curriculum, but they're being added now into the A-level curriculum. So the name ending is what I wrote first, and then this was an example. Example name. And you'll see these names shortly as we start to look through questions. I'm going to pause again. You'll see some writing. We're good. So this is actually a review from last year of hydrolysis. Hydrolysis means to put in with water. Hydrolysis can happen, and the keywords you're going to want to circle are in acid or in base. And if you hydrolyze with acid, you get one key difference than hydrolyzing with base. In both scenarios, you have to break your molecule apart, whether it's an ester, an amide, or an acyl chloride. You always break apart in the same spot, right next to the C double bond O, and in between that carbon and the electronegative element. It's always this bond that gets broken, and you separate into 2 products. On the O side, C double bond O, you put the OH back. On the alcohol or the amine side, you would put the H back. So basically what we learned last class, where you take the OH out of in a condensation would be where you put the OH back in a hydrolysis because they're inverse processes. So the difference, if I have a base, you don't have enough acid to get the carboxylic acid. So instead of OH, you get ONA. So the key difference in a base is instead of OH, you get ONA. And we'll take a look at practice examples of this very shortly. And again, these reactions were actually part of AS chemistry, but it's been a while since you've seen them. We learned them back in February of last year. Hydrolysis of amide, same idea. The bond that you break is right there. The OH goes to the side with the C double bond O. And a hydrogen goes to the side with the amine. So your products would be the OH goes to the carboxylic group, the C double bond O, and then the H goes to the amine. Now basically break apart and you have to know where to put each thing. If it's an acid, is this in acid? Is this reaction happening in acid?
Yes.
Acid. Then you know you're going to get the OH. If it was in base, what would this have been instead? So if it had been an NaOH, the same reaction, what would be the alteration to the products? It would have been instead RCO, O minus, Na plus instead of OH. ONA, we called it. And then this other part would remain the same. It leaves your amine or your alcohol completely unaffected. It's only the carboxylic group that's affected by whether it's an acid or a base. When we get to organic part 2 in unit 6, I'm thinking about devising some type of competition for that. So we're not going to do it in unit 5 because there's really not a ton of reactions here. But unit 6 is all about the reactions, just like it was last year. And so I'm going to work on something for you all. We'll see. I'm also working on something for AS chemistry. Revisions to competitions. Ready to continue? Do you think you should maybe put this on a flashcard or in some revision notes? For unit 6, I'll give you flashcards. Again, there's not a ton of reactions in this unit. This is one of the main ones. There's a few reactions, but when we get to more reactions, then I'll give you some flashcards to work with. All right, so I have some practice questions because we could talk about it, but we need to see practice. And so first question here says to draw the displayed formula of propanoyl chloride. Let me say this is in acid. Draw the displayed formula of propanoyl chloride. So what does prop mean? 3 carbons. Displayed means what? I'm gonna put a circle around displayed because it's a specific thing I'm being asked to do. Displayed means I must write out every single hydrogen, every single carbon, every single bond, right? So it's going to be CCC. Typical convention is to put the group on the right-hand side. It's just easier to write. And so CCC, and then this would be the O and the Cl for the propanoyl chloride. This is the functional group. But what else do we have to do? With all the H's, right? So until every carbon has how many bonds?
4.
And if we put one carbon with 5, the whole thing is wrong. Because this only has 4 valence electrons and cannot break the octet row due to it not having access to d orbitals. And that's no, no carbon with 6 bonds. Don't do it. So this would be it for propanoyl chloride. Yes. Now show the hydrolysis of propanoyl chloride, and I'm gonna say to do it in acid. So propanoyl chloride, same thing we had here. However, this I don't need to show displayed, except I like to only expand around my carbon of interest. I don't know if you remember me saying that word last year. Carbon of interest is the only one that matters in the chemical reaction. Like, this stuff isn't reacting. The hydrocarbons are famously unreactive. So this is the only part that's going to be reacting. And we said it's going to be an acid. If we don't specify the acid, what do we write? So this is going to be H plus, and then hydrolysis means we're reacting this with what? Water, right? So what are we going to get as our products? The bond that breaks is there. What part of water goes on the C double bond O side? So OH would go there, and H will go there. And what are my products? CH3, CH2, CO, OH, a carboxylic acid. And the other one, let me change the color. Plus, you think this is pretty acidic. You're making a carboxylic acid and you're making hydrochloric acid. Do you see that? Like, if you think about that, this reaction is probably one I would be wearing my gloves or goggles and lab coat in a contained area. But this is what you're getting out of it. Notice what I did was color coded. The H that I'm adding, I put here. The OH I put here. So you know that this is the water that's going in and breaking up the group. So if you want to take a picture of it, you can. I am also recording. So if you need to go back and see it, I'm going to try to be careful to color code things. So it makes more sense. Good so far? Does this reaction ring a bell from last year? It is a type that we did cover. I think it was not on the day of college tour, but it would have been around that time that we usually cover it. I never teach a lesson on the day of college tour because a lot of juniors will be out that day. Same thing for this class. If a lot of people are going, you'll have to let me know if you're going on college tour. All right, so what I wanted to do, why you see a blank slide here is I just wanted to go over some practice questions with you. On your homework, your first homework questions are going to be practice questions on hydrolysis. So I just wanted to throw some out. If you recall how we did with the quizzes last year, you had the quiz competition for public subs. I would just write out a bunch of questions and then you would have to solve them. I told you I'm not doing that for Unit 5, but I'm working on something for Unit 6. So just so you can get the practice leading up to it. And even though this is not part of Unit 6, I probably will include these reactions as well because all of organic really exists together. So just a heads up. All right, so let's try this. I've got this going on, and I've got this going on, and it's in NaOH. Can you come up with the answer? Write it on your paper. Do the hydrolysis. It doesn't say whether you have to do it in skeletal, structural, or displayed, so I usually suggest just doing it in whatever format has been suggested to you. See if you can figure out the product here. Do you know which bond to break? Write yourself first. If you write it like that, it suggests that the hydrogen is connecting to the carbon and the oxygen. Right? So, you know where to break your bond? It's between the carbon of the carbonyl and the single bond electronegative atom always. And then we have to decide what goes on what side. And so it's kind of easy to remember with NaOH. Na is going to be part of the equation. It's going to be ona, right? And then the other side will have still the hydrogen. And so just to write it out, it's going to be, let me change the color black. I want it to be color coded. The group I had originally was this. And then what's the new thing that I'm adding in? technically, the O, no. So that should be one of my products. Does that make sense so far? The other product is H goes on the side with the alcohol to return it to an alcohol. And so this will become H. Let me kind of put it back to the stuff I had before, and then this. You can see what's going on. If I have hydrolysis in a base, I do not get the carboxylic acid. Instead, I get UNA or the O minus Na plus. If it was a acid, it would have been OH. Yes.
Oh.
Yeah, that's right. All right, we'll try another one. This one not in skeletal. This one we'll do in structural. So try a second question.
So the owner goes in that sentence, it's base,
Yes.
and if it was acid, it would be
Then it would have been OH. So carboxylic acid does not exist as an acid in base. The H plus is dissociated. So instead of being COOH, it's COO with the Na plus from the NaOH. The carboxylic acid can only be a carboxylic acid in acid. And that's going to be a theme that runs later on in today's lesson. My eyes were like that when I like the first hour I was here, I was having a struggle. It's a struggle. Tomorrow will be a struggle too, because most of us, or many of us, will be here till 8 p.m. or 7:30, something like that. Induction. Induction is today, so tomorrow will be a struggle because like you're gonna be here late and then you're gonna come back in the morning. So it'll be a struggle. No? Okay, sorry. Anyways, so let's continue. Next one. This one I said I'm not gonna do skeletal, I'll do this one structural. So CH3, CH2, CO, and let's switch it up a notch. NHCH3. And then this one we're gonna do, and I'm just gonna write it like this. We'll do an acid, and it's a hydrolysis, so I gotta put the water around. You may see the water written as reactant, you may see it above or below the arrow, but the water is there, it's aqueous. These solutions are all aqueous, so the water will be there to hydrolyze. So try this one, see if you can come up with the products. Reese is about to go over that point like next week. Like water is liquid. I think I've already told them, but like we're gonna make it more apparent when we do reactions. Water is liquid. Something dissolved in water is aqueous.
Yeah.
That's definitely.
Yeah.
That's okay.
All right, are you ready? So where is the bond that we break?
I thought Brian had. See.
So remember, it's always between the carbon and that has the double bond and the electronegative group right next to it. That's always the bond that breaks. So right there. The OH will always go on the side with the carboxylic group. And the H would always go on the other side. So when we look at the hydrolysis, the HOH, we know that the OH should go here. And the H should go there. When the bond breaks, those are the new bonds that form into place. And so to look at what will our new products be, and hydrolysis should always have how many products? 2, right? You're going from one starting bigger molecule to 2 smaller molecules. And so you get CH3, CH2, CO, new group is, or new bond formed is right there, OH. And then on the other side, it would be plus H. And then I show all the stuff I had before. And H, and then CH3. So hopefully you can see clearly this is the bond being broken. And then this is the new bonds that are being formed. And then it's water that's going into the molecule. That's why we call it hydrolysis. Good? So we've done 3 examples. I think we're good to move on. The other major topic for the day. So the one major topic I wanted to cover was to go over this reaction with hydrolysis, but not only including the esters that we did last year, because we only did hydrolysis with esters last year, but also to include amides and acyl chlorides, which are these 2 new functional groups. Now, the final topic we have today is the biochemistry topic, which if you haven't taken ACE biology, you haven't seen probably much since you took pre-ACE or honors biology. So let's talk about amino acids. In this course, you are going to be required to recognize the structure of an amino acid, meaning that you need to know that an amino acid has 4 components. And if you read the name and you know your functional groups, you're already going to know 2 of those components. Amino means you have an amine in a amino acid. And an acid, what's the only functional group that has the name acid? Carboxylic acid. So an amino acid always has an amine and a carboxylic acid. A carbon in the middle. A single hydrogen is always there. And then something called an R group. Do you remember what the R group is? The rest of the molecule. And it's the R group that gives different amino acids their specific properties. You may remember amino acids are the building block of what we call proteins. Proteins are extremely important for your bodily function. If you do not have all 20 essential amino acids, you'll be pretty bad health and health-wise. And so there's something called complete versus incomplete proteins. If you are vegan, you have to pair foods together to get the complete proteins, because complete proteins are typically found in meat and meat products. And so our body makes 11 amino acids, but the other 9 you have to get from your diet. And so it's interesting. There's a bunch of interesting things about amino acids. Biochemistry is actually a super fascinating topic. If any of you do go on to study AS Bio, and you like chemistry, the biochemistry component will be the most interesting to you, because it has a lot of chemistry basis in it. But they are the essential building block, and most people who go on to want to be doctors, if they want to be doctors, most do end up majoring in biochemistry, which is basically a marriage of a biology major and a chemistry major that focuses on like the reactions in your body. All right, so it's the essential building block of proteins. All of them have a carboxylic acid and an amine, which is significant chemically wise, because amines are bases. You're going to want to write this down. Amines are bases. And maybe you remember this from the first unit this year. We learned what would the requirement for a base be. It has to be able to receive what? And it can. It can receive H+, because of that pair of electrons can always receive H+. So bases, because they can receive H+. We want to write that at the top. They can always receive H+. Carboxylic acids are always, what do you think? Acids. So carboxylic acids are acids. That's so silly to say, but there's a point. Which means they give away H+, right? They have the ability to donate H+, because of the H+ in it. They donate H+. So amino acids are fascinating because they have an acid component and a base component, which means technically it could give away an H+ from part of the same molecule to another part of the same molecule. It can function as an acid or a base, which also means it's amphotericity.
Also,
Carry.
it can donate to itself.
It can donate to itself, and you're gonna see that happen shortly. Actually, it can donate to itself. It can go like, whoop, and then transfer the H plus right there. And it will. In certain solutions, it will donate the H plus to itself on a different part of the molecule. So that's why I said it's one of the fascinating aspects. It can serve in a Bronsted-Lowry acid-base reaction, both as the acid and as its own base. Which basically means you're transferring the H plus from one part of the molecule to another part of the molecule. And so we're going to take a look at that process today. To be aware of when this happens, when this specific process happens, when the H plus is given from the carboxylic acid to the amine, this is actually what we call the zwitterion. So a zwitterion means that you have transferred the H plus from the carboxylic acid to the amine group. In a neutral pH, and so we're going to be looking at solutions of different pHs. In a neutral pH, which is the pH of pure water, an amino acid would exist as the zwitterion. Why? Because in water, the acid will act as an acid, which means it does what? Gives away H plus. And the base will act as a base, which means it receives H plus. So this is how amino acids appear in aqueous water, right? Solutions. Other biochemicals do interesting things as well. For example, sugars in water will actually condense and form a ring. So anybody who studied biology has seen sugars in rings. That happens when the sugars are in water. They condense. Continue. Are we okay with this idea? So you are going to be asked, and I believe it was the first standard that we read, you're going to be asked to predict an amino acid structure based on whether it is in a neutral pH, a low pH, or a high pH. So looking at this, what does a low pH mean? Lots of H plus, which means that both functional groups will be acidified. So if there's lots of H plus, both functional groups will exist in acid form. Meaning, there's so much H plus that the base can receive an H plus. There's so much H plus that the carboxylic acid can keep its H plus. Everything that can have an additional H plus does have an additional H plus in a low pH. So you would get the Cu, and you would have NH3 plus. And you'll notice in this graphic they referred to, you would have a cation at the end because it only has a positive charge. The amino acid has a net positive charge. And that's going to matter because we're going to have to do something with charges next class. Zwitterion is at what pH? This will be where our pH is neutral.
Do we have to know like the exact values, like 0 to?
It's going to depend on your amino acid because amino acids have different neutral pHs that they exist as. Because of the R group being different, it can affect the acidity of the overall amino acid. So no, you do not. The quick answer is no, you will not have to memorize exact pHs. You'll see questions where you look at ranges pretty much. And then you will predict from the ranges if it's a low, neutral, or high pH compared to what it's supposed to be. So the zwitterion is wherever neutral is. Neutral has a fancy name. It's called the isoelectric point. That was also mentioned in the standard, and we'll see it, I think, shortly. If not today, then next class. In the zwitterion, you have COO minus and NH3 plus, meaning in the zwitterion, the carboxylic acid has transferred its H plus to the amine group. So the acid gave away its H plus like it's supposed to, and the base gained the H plus like it's supposed to. And at the end, what's interesting is that this overall amino acid, what's the charge?
Neutral.
It's neutral. So the Zwitter ion, you need to know the overall charge is also neutral. So in acid, your amino acid will have a positive charge. At what we call the isoelectric point, there's neutral. The Zwitter ion is neutral. And when we have a high pH, what does that mean? There's very little H plus, right? And what is there a lot of? So there's very little H plus. We don't know what very little is, but it's very little. There's not H plus going around there, not much. But there's lots of OH minus. And because there's lots of OH minus, all of the acids will give away their H plus to the OH minuses in the solution. Does that make sense? Because there's lots of OH minus, the NH3 plus, it'll lose its H plus, and the carboxylic acid will lose its H plus. So it will exist as a anion with a negative charge. And so in a high pH, you have COO minus and NH2, which is the basic form of both functional groups. Whereas over here, you have the acid form, where they both gain the H plus because of all the H plus available. And so you will have to predict the acid form, base form, and Zwitter ion for an amino acid based on pH. Which is really just Bronsted-Lowry theory. It's really just Bronsted-Lowry theory from Unit 1, which we will be revisiting in practice questions. All right, so we're going to start looking at the checkups from the textbook. And I think I do not have that many Cambridge questions today. There will be next class. Not really many in today's lesson. We're just initially learning this. What is the general structural formula of a 2-amino carboxylic acid? So this is just what is the general formula for an amino acid. What goes in the middle? A carbon. Carbon's always attached to 4 things. In an amino acid, 3 of those things are always the same, and 1 of them changes. What are the 3 things that are always the same in a carboxylic acid? An amino acid. COOH, that's 1. What's the next thing that's always the same? NH2, that's 2. Notice I don't put the hydrogens next to the carbon because I don't want to suggest that the hydrogens are bonding to the carbon in the middle. What goes on top? Hydrogen. Nope. You could break any of the 4 on any side you want because free rotation.
Like we put the H to wait, and to H. Wait,
NH2.
you know what I mean, yeah.
They might have wrong.
Really?
You cannot put hydrogens in the middle. You have to put them on the outside. And then R, where R could be anything. Could be 20 different things for the 20 unique amino acids. Are we okay with this general structure? Next question, why are they solid? Suggest why they're solid at room temperature. They're in the solid form. They exist in the solid phase, not a liquid, not a gas. Why do you think that amino acids, based on anything that you've learned in chemistry about their chemical structure, what suggestion could you make that they exist as solids? What is the why? I'm talking about dissolved in water just as they isolate themselves. They exist as solids. I mean, when you have the protein isolates, they're like a bunch of amino acids together, which anybody who tries to get gains in the gym probably has protein powder. Because of lots of hydrogen bonding. That is correct. Peter has it. So due to multiple hydrogen bonds, right? Due to multiple hydrogen bonds. Remember, the stronger the attraction, the hydrogen bond is the strongest of the intermolecular forces. The stronger the attraction, the more favorable a condensed phase is. So I'm going to write underneath stronger attraction favors condensed phases of matter. Water has hydrogen bonding and is a liquid, but it's actually a super small molecule. It's only got 3 atoms. So this has way more than 3 atoms. This has at minimum 3, 4, 5, 6, 7, 8, 9, and 10. At minimum, it has 10 atoms. It could be 20, 30, 40 atoms. So it's way larger than water. It has multiple hydrogen bonds. Therefore, it is likely to be a solid. That's the idea. So the answer, every time we talk solid, liquid, gas, the answer always lies in what? The intermolecular forces, the forces of attraction. So that still holds true. Back from AS chemistry, whenever we talk about states of matter, we must answer in regards to ion forces that hold the molecules together. Like, all right, so good so far? I'll pause. See some writing, so I'll pause. All right, so on the next checkup, you're going to be given an amino acid. They said draw the displayed formula for the amino acid called serine, and the R group is this. So remember, 3 groups are the same, and the only thing that changes is the R group. So you would start by writing your C, your H2N, your H, your COOH, and what would you write at the bottom? The H2OH. In that order, the alcohol at the end. It suggests here you're connecting to the CH2. Now here's where it starts to get important. The second question that comes off the first one says to draw the Zwitter ion. Can we draw the Zwitter ion? What would that look like instead?
Would it go to these CH2s and not complete, or would it go to the
Right, just
The Zwitter ion goes from the acid to the base. Which one is more basic, an alcohol or an amine? It's going to be the amine. The amine is the only technically classified base of the functional groups.
So
Therefore,
unless
you
it's,
would show, unless there's an amine here,
unless it's low pH and we go to that right first.
it goes to the amine first. And so here it's the Zwitter ion. So this is going to go right here. But this is actually an H plus that we're transferring, right? So what would we write as our product? What would the Zwitter ion be? Instead of H2N, it would be 3 hydrogens on a nitrogen, right? But that would have a plus charge because the H plus is going there. So it would be H3N, and then this should be plus because that's where you added the H plus. And acid is H plus. You're transferring H for the positive one charge. So it goes here. And then this Zwitter ion always transfers from the acid to the base. And then you have COO, and then what would the charge of that be? If it lost H plus and it was neutral, the COO must have been what charge? Negative. And so it still is negative. And it's the really important thing here that you include both charges because the Zwitter ion, remember, is electrically neutral at the end. Positive and negative will cancel each other out. Yes? So that's a Zwitter ion. Now, I believe in the next question, we're going to look at the different conditions. How would this look in acid? How would this look in base? So start with your Zwitter ion. That's this. In acid, what would you write? How would you change the structure of serine? Acid means what? Acidic conditions. H plus everywhere. Low pH, right? So how would this structure be affected? This was neutral pH. You add the H plus wherever you can, right? This one already has the H plus. So what still needs more H plus? The carboxylic group, right? So therefore, at low pH, you would write it as H3N plus. This would all be the same. But instead of COO minus, this would now become COO H, and I'll change the O. That's the extra H. So every group that could be an acid or a base exists in its acid form if there's lots of H plus in the solution, because H plus is donated everywhere it can be donated. Kind of make sense? Whereas in the base form, you take away H plus to give to the OH minus. Alkaline conditions means lots of OH minus, right? Means take away H plus from every group that could be an acid or base. You're going to get the base form, which means it loses its H plus to go to the base that the solution is. So then what would this exist as then in base form? Would this be NH3 plus or would it lose the H plus? So this would go back to H2N. The hydrogen group is unaffected and the side group is unaffected. If the side group was a carboxylic acid, would it be affected by this process?
Yeah.
It would. All acidic groups would lose their hydrogen. So if your side group happens to be an acid or base, you have to do that for your side group as well. Here it's not, so you leave the alcohol as is. And then this would be COOH or COO minus. It's in base. So you have to take away the H plus from everything you can. Can you take away an H plus from a carboxylic acid?
Yeah.
So you would get the COO minus. This would be the correct answer. This is how the Cambridge questions are too. Where they'll ask you for the different variants of an amino acid. But not only one, it might be more. So far so good? All right, so the next checkup is going to discuss how to put together a dipeptide or a tripeptide. So basically, how do amino acids link with each other? You may recall this in biology, called your primary structure of a protein. Do you remember that protein had different structures? And there was a primary structure, a secondary structure, a tertiary structure, and a quaternary structure? You do not have to memorize all the structures for this class. You would for AS biology and all their linkages, but we're going to go over how to link amino acids together. What is the chemistry behind that now? So the R groups in 2-amino carboxylic acids, which is just their name for amino acid. It's an amino acid. For alanine and valine are these 2 R groups. Draw the structures for both of them. So the regular amino acids. So draw them both first. So this is the R group for one, and this is the R group for the other. Let's draw them both. So it would be CH, NH2. It did not say zwitterion, so we're just drawing the basic one. And then the first one is CH3. And then I put plus. The other one is H2N, CH, COOH, and this is CH, CH3, CH3. That's us. Or you could leave it in the parentheses and write the CH3 too after the CH. That's fine. So draw the structures of amino acids is the first question. Afterwards, we have to link these together. So from what you learned last class, this is actually just a condensation polymerization. Meaning, you're going to take away the OH from the carboxylic acid, and you're going to take away a hydrogen from the nitrogen. So on the next question, which it'll say, it says, give an equation to show the formation of a dipeptide. So circle this dipeptide. That means how many? Di means 2 linked together. So unlike condensation polymerization, you will not have dangling bonds. You will not have a little N on the outside. Why not? Because you're only putting 2 together. So dipeptide means you have a total of 2 amino acids. So you're going to link them together in the middle, but you don't have dangling bonds. So let's see, how do we link these two together? I'm gonna rewrite them, but what I'm gonna do is I'm gonna write out, I'm gonna expand my COOH and I'm gonna expand my NH2. Because when you write a peptide bond, you have to fully show it. Which means the bond that links them together, you have to always fully show that, just like in the bell work. So I'm gonna rewrite this, H2N, CHCOOH. Notice the part that I fully write, this part, the carboxylic acid. It doesn't really matter if you write everything else, but this part matters. Because remember, I'm going to be removing water to put them together. So that's the one. The other one is this one. I expand only the part that I want to do the reaction for. So that's the NH2 part. Get that a little bit nicer.
Where does the H come from? From the carboxylic or the?
To take away the water from the, I'm going to show that now. So this would be CH, this is the CH. If you want to write it as CH3 too, instead of expanding it out, you can totally write it like this. This is the same thing that that is. And then this is the COOH. It said write an equation. So there's my arrow. I'm going to pause to give you some time. Now, how do I merge these two groups together? How do I put these together to form one big molecule? I have to remove what? Water. And from the same spots we learned last class. The OH has to come from the carboxylic acid. So there is no OH on the other side anyways. So it's kind of hopefully apparent. The OH comes from here and the H comes from there. The clearer you draw it, the clearer you'll understand your answers. And so then if I'm removing water, I'm going to have to link this molecule together with that molecule to complete the octet rule. So then I merge them together. I rewrite everything else the same. I have to be meticulous and careful that I don't miss any atoms. So I rewrite everything. So this is going to be H2N, CH, CH3, C double bond O. Where the OH and the H were, what do I link to now?
See,
The C and the N. And I'm going to write this in a new color because that's the new thing, right? The C is linking to the N, H, C, H, C, O, O, H, and C, H, C, H3. So everything else gets written the same. Typically, there may be a point where they ask you to label the peptide bond. Where would the peptide bond be? It's this red one. So this is called the peptide bond because it links the amino acids together. Bond is a new bond formed that links the amino acids together. That links individual amino acids together. So it's actually called the amide bond. The bond that makes it an amide is called the peptide bond. This is a dipeptide because I link together how many amino acids? 2. When you observe the standard that was at the beginning of the class, it said you may be asked to construct dipeptides or tripeptides. So either you'll have to link 2 together or you'll have to link 3. If it was 3, you would just put one more, like add one more amino acid and then you link them and link them again. And so that's all you'd have to do if it was a tripeptide. It's the same idea. So what type of reaction is happening here? This is called a condensation, right? So this is actually a condensation because you're removing water. Yes. So that's interesting. The word I want to say is a fancy word, but actually it's a little bit too small to like go, there's too many atoms for it to do that. Like, I get what you're saying because it kind of has that bidentate thing from the ligands, if we were talking about ligands. But these electronegative groups and these electronegative groups will actually kind of repel each other, and it won't do that. Because there's too much electronegative groups in here for that to happen. But that is an interesting question. An interesting question. But no, it doesn't. All right. So a couple more factoids before we leave out for the day. And then, like I said, I did have a game that I want to do all the time because you need to practice your functional groups, don't you? You know you do. You know you need to practice functional groups. And instead of making an assignment, I want to do something a little bit more fun since we have a little bit of time. But we have a couple of more things to cover. So peptide bond, I already covered what this is. That is this specific bond right there is called the peptide bond. And another name for the reaction is called condensation. We already said that. This reaction can happen again and again and again to form many amino acids linked together. And this is how we get the primary structure of a protein, is when it's, I've read research, they usually classify the protein when it's 50 or more amino acids linked together. So basically this process 50 times. And your body does this. I mean, like, I think it's synthesized protein synthesis is in your mRNA. Correct me if I'm wrong. But your messenger RNA, it happens. You have protein synthesis in that area in your cell, and your body does this actually. All right, continue. So then the next thing I wanted to talk about was just the different types of R groups that exist. And so, good news, you do not have to memorize all 20 R groups. Bad news is I did. Like when I was a student in biochemistry, if you study biochemistry in your future life, you may be asked to memorize 20 amino acids by heart. But what you should be able to recognize is you should be able to group the R groups into type. You should recognize if your R groups are nonpolar, which means they're just hydrocarbons. If they're polar, which means they have an electronegative group on them. If they're acidic, meaning they have a carboxylic group on them. Or if they're basic, meaning they have amines on them. And so you should be able to recognize based on your R group if it's nonpolar, polar, acidic, or basic, based on what the R group is. Once again, you do not have to memorize any of the R groups, but you should know like their basic characteristics and differences. And so this is just what the protein structure looks like. You should recognize it. When proteins are coded, it's just joining a bunch of amino acids together. And so this is what it would look like. And then these would be all your different R groups. And then each of the individual proteins have different functions in your body. All right, we already covered hydrolysis. Peptide bonds can be hydrolyzed. Why? Because remember what we said right at the beginning? The requirement to be able to hydrolyze a bond is to be able to break that carbon single bond electronegative atom next to a C double bond O. So proteins can be hydrolyzed, and they are hydrolyzed in the process of base or acid under reflux. And that's it for today. So let's see if we can pull up a quick game on functional groups. So I had bought, because I want to test something out, I had bought a full Kahoot subscription in December. And so there are actually different game modes in Kahoots that I've never seen before. And so I wanted to see if there's any that are interesting. So you would be the first test group piloting this. And so they give us, there's these different game modes. One of them's called Robot Run, Lost Pyramid, Submarine Squad, Cosmic Conquest, Color Kingdoms, Treasure Trove, Tallest Tower. I don't know what killer it is. But there are various ways you could play. There's also, I don't know what Winter Holidays is. What's that? Is that just normal? I think that looks normal. There's team mode. Let's take a look at this one. Work together with your team to build the tallest tower. Answer questions correctly to make your tower the tallest. Let's try this one. So we'll do a 10-minute game just to try it. Yeah, it's gonna split you into teams. Yes. You can scan, show, and go. So everybody does need to participate. It'll be a participation rate. If you don't get everything right, don't stress. All right, so we've got some teams. Make sure you're entering the code 990972. 990972. I do not believe you need to join a class or anything. You just put in the code and write your name, like your real name. Code is 990972. Go ahead. You can take the class. Yes.
Or like initial in order to answer them or no?
It's just going to be typical Kahoot where they give you the answers and you pick the right one. You won't have to draw anything out. It's just to guess functional groups. I just want to test the game mode to see if it's good. So you're my first pilot for testing this. All right, still waiting for a few people. Julio,
Just press it.
Alexander,
No.
Julio.
I think it's like they put you in the groups.
Don't leave Damani and Rosalind without their team member.
Oh,
Pretty sure that's where you're gonna go. Don't work on the computer? Is that a school computer? Just need to enter the key code. Yep. All right, so let's check it out. Let's see what it does. Get ready to, with your team to build the tallest tower. You want to see the tutorial?
Yes.
How to play. So I guess you build, answer questions correctly, get building blocks, drop blocks to build as many floors as you can, stack blocks up to the bonus for a power up. All right. Let's see. Take this off. All right, I'm gonna get off the mic.